Okay, so we have a quantum and nonlinear photonics practice final exam. So let's begin. So starting from Maxwell's equations in a non-magnetic dielectric medium with no free charge or current, derive the nonlinear wave equation for the electric field in the presence of a nonlinear polarization. So we're given here that equation for nonlinear polarization show explicitly that the electric field satisfies this very familiar equation here. Then separate the equation into linear and nonlinear contributions and discuss the physical significance of that P sub NL. And I'm going to go through this rather quickly. I won't read through the entire practice exam. The work is there. Some intermediary steps are skipped over, but this serves as a reference for you to practice. Okay, so Maxwell wave equation in nonlinear medium, very, very famous. In a source-free non-magnetic dielectric, okay, we're given this cross product here. These should look very, very, very familiar. What we're going to do is take the curl of Faraday's law here, okay, and since our magnetic field is equal to mu naught H, the cross of del in the magnetic field is mu naught del cross H, that equals mu naught partial dd dt, and therefore we're going to get this cross product here. We have del cross E, that equals negative mu naught second partial d with respect to t. Okay. Now, using this d equals epsilon naught E plus p, we get this again. This cross product here. That's going to equal negative mu epsilon naught second partial E with respect to t minus mu naught second partial here p with respect to t. And using the vector identity here, this cross product is equal to del times the quantity, the dot of del in E, minus del squared E, and assuming transverse propagation so that del dot E approximates 0, we get the following. Very famous equation here for this negative del squared E. And just as a note here, in inhomogeneous or strongly nonlinear media, that dot of del and E may not vanish exactly. Okay. So we get this following, that del squared E minus mu naught epsilon naught second partial of E with respect to t equals mu naught second partial of P with respect to t. So now we write our formula for our P for our nonlinear polarization. And for an isotropic linear medium, okay, we give that first order polarization equals to epsilon naught chi first order E. Then the linear part modifies the refractive index here. The n squared equals 1 plus chi first order. The wave equation becomes the following. That del squared E minus n squared over c squared, second partial v with respect to t equals mu naught second partial of p sub nl with respect to t. And the nonlinear polarization acts as a source term that generates new frequencies, modifies phase, and couples optical waves. And again, I'm just going through this rather quickly so you have it as a reference. Okay, so number 1, let's move along to number 2. Whoops, sorry. Okay, number 2. All right, so just getting this in focus. Sorry about that. So number 2 we'll do in components here. Consider a bound electron in an n harmonic potential. V of x equals 1/2 m omega naught squared x squared plus 1/3 alpha x cubed. So let's read out everything we have to do, and we'll do this in the parts. Monochromatic field, E of t equals E naught cosine of omega t. That drives the oscillator. For part A, derive the equation of motion including the nonlinear restoring force. Part B, use perturbation theory to solve for the first order displacement. Derive the second order displacement. Show explicitly how second harmonic generation arises. Obtain the scaling form of the second order susceptibility, and discuss why centrosymmetric media have vanishing bulk. Okay, so we're just going to do this in parts. So second order susceptibility, and just as this is a reference, A through F, we're just going to go through this whole thing here. Okay, so starting here, second order susceptibility, microscopic origin of what we have here, our second order susceptibility. The potential has the following: V of x equals 1/2 omega naught squared x squared plus 1/3 alpha x cubed. The force is given here as F equals negative dV dx, and that's negative m omega naught squared x minus alpha x squared. Okay, the driven equation of motion is then m x double dot plus m omega naught squared x plus alpha x squared equals negative e lowercase times uppercase E of t. Let x equal the series of first order plus second order plus on and on and on. The applied field is E of t is E naught cosine omega t. At first order, m x double dot plus first order plus m w naught squared x first order equals negative lowercase e capital E sub naught cosine omega t. And from here, we're going to assume this x first order equals a cosine omega t. Okay, then what we could say here is that m omega squared a cosine omega t plus m omega naught squared a cosine omega t equals negative lowercase e capital E naught cosine omega t. So we could factor here m times quantity omega naught squared minus omega squared a equals negative e capital E naught. So that first order there, x first order, is going to equal to this negative lowercase e capital E naught over m quantity omega naught squared minus omega squared cosine omega t. Okay, all right, so that's that first order. At second order, we have m double dot second order plus m omega naught squared x second order equals negative alpha x first order squared. So x first order squared equals a squared cosine squared omega t equals a squared over 2 times the quantity 1 plus cosine omega t. Okay, so m x double dot second order plus m omega naught squared x second order equals negative alpha a squared over 2 times the quantity 1 plus cosine 2 omega t. So the second order displacement contains a dc part and a 2 omega part. And x second order is b naught plus b2 cosine 2 omega t. The dc part is going to satisfy this m omega naught squared b naught equals negative alpha a squared over 2. So isolating b naught is negative alpha a squared over 2m omega naught squared. Okay, so the 2 omega satisfies m times the quantity omega naught squared minus 4 omega squared times b sub 2. That equals negative negative alpha a squared over 2. So isolating b sub 2 equals negative alpha a squared over 2m times the quantity omega naught squared minus 4 omega squared. So, okay, we get for our second order here, x, second order displacement here, we get negative alpha a squared over 2m omega naught squared minus alpha a squared over 2m times the quantity omega naught squared minus 4 omega squared times cosine 2 omega t. Okay. And moving along, the 2 omega term produces second harmonic generation for n oscillators per unit volume. So P equals negative NEX. And since that x second order is proportional to E naught squared, that P second order is proportional to E naught squared with scaling. Okay. And that x second order is going to be proportional to NE cubed alpha over E naught m squared times the quantity omega naught squared minus omega squared, that quantity squared, times the quantity omega naught squared minus 4 omega squared. Okay. And here, last component in central symmetric medium, reversing E to negative E should reverse P to negative P, but a second order term behaves as E squared, which does not change sign. Therefore, that bulk, that second order here, or the chi, second order chi 2 equals 0 in centrosymmetric media. And just a note here, up to sign and numerical factors depending on your convention when using this. So number 2, very interesting problem, canonical. Moving along now to number 3. Okay, number 3. Okay, so number 3, a nonlinear crystal with susceptibility given here for second harmonic generation is used for second harmonic generation. Assume the pump field is given here for E sub 1 ZT given here. And generated second harmonic field is E sub 2 Z of T given here. Okay. Part A derived, so let's go through all these, part A through E. Part A derived the coupled wave for A sub 2 of Z under the undepleted pump approximation. Part B define the phase mismatch parameter given here for delta K. Part C show that generated intensity scales that I sub 2 omega is proportional to sinc squared of delta KL over 2. Part D, explain physically why phase matching is essential. And Part E, describe one method used experimentally to achieve phase matching. So second harmonic generation and phase matching problem. So I'm just going to go through this. Nonlinear polarization at 2 omega is this. That E naught chi second order E sub omega squared with E sub omega equals A sub 1 E to the I quantity K sub 1 Z minus omega T plus CC. Okay, so here the square contains that E, so that E omega squared, okay, or contains that A sub 1 squared E to the I quantity 2 K sub 1 Z minus 2 omega T. So this second order P up to 2 omega equals epsilon naught chi second order here, A second order, A sub 1 second order E to the I times quantity 2 K sub 1 Z minus 2 omega T. So we're going to let A sub 2 omega equal A sub 2 of Z times E to the I quantity K sub 2 Z minus 2 omega T plus CC. Okay, using the slowly varying envelope approximation, dA sub 2 dZ equals I kappa A sub 1 squared E to the negative E I del KZ. So our del K is going to be equal to K sub 2 minus 2 K sub 1. And that kappa is the coupling constant proportional to that second order chi. Now, if we integrate from 0 to L, we get A sub 2 of L equals I kappa A sub 1 squared from 0 to L E to the negative I delta kz dz, and the integral is 0 to L e to the negative I delta kz dz. That comes out to, we skip some steps performing the computation. That's LE negative I delta KL over 2 sinc of delta KL over 2. Okay, so we could say a sub 2 of L is I kappa A sub 1 squared L e to the negative I delta KL over 2 sinc of delta KL over 2. All right. Intensity is proportional to the magnitude A sub 2 squared. So I sub 2 omega is proportional to this L squared I sub omega squared sinc squared of delta KL over 2. Phase matching is essential now. Phase matching is essential because if delta K is not equal to 0, generated waves from different parts of crystal interfere destructively. Efficient buildup requires delta K be equal to 0. And experimental phase matching can be achieved using birefringence, temperature tuning, angle tuning, or quasi-phase matching. Okay, so that's number 3. Okay, moving along now to number 4. Okay. So number 4, consider 3 interacting waves satisfying omega sub p equals omega sub s plus omega sub I. Okay, so let me read through these. Part A, explain the physical difference between these 3 different frequency generation, DFG, optical parametric amplification, OPA, and optical parametric oscillation, OPO. Part B, starting from the nonlinear term, this P second order proportional to chi second order E sub P, E star, E sub S star. Derive the qualitative form of the Idler generation equation. Part C, explain the role of energy conservation and momentum conservation in parametric interactions. And part D, discuss gain saturation in an optical parametric amplifier. So this is a difference frequency generation and optical parametric amplification problem. So going through it here, DFG, OPA, and OPO, the 3 frequencies satisfy that omega sub P equals omega sub S plus omega sub I. Difference frequency generation means a pump and signal combined through that chi second order to generate an idler, that W sub I equals W sub P minus W sub S. Optical parametric amplification means a strong pump amplifies a weak signal while generating an idler. Optimal parametric oscillation means the gain medium is placed inside a cavity and above threshold. Okay, the signal and or idler oscillate without a strong injected signal. The relevant second order polarization is this. That second order P sub I is proportional to E naught, that second order chi, E sub P, E star sub S, let E sub P equal A sub P e to the I, times the quantity kpz minus omega p sub pt, and E sub s equals A sub s e to the I, quantity ksc minus omega sub st. Then we get E sub s star equals A sub s star times e to the negative I, quantity ksc minus omega s sub st. This drives the idler frequency, omega sub I equals omega sub p minus omega sub s, with the wave vector k sub I is approximately k sub p minus k sub s. The idler amplitude obeys. So we have this, our derivative d a sub I dz equals I kappa a sub p a sub s star e to the I del kz, where del k is that k sub p minus k sub s minus k sub I. All right. in the last components, energy conservation is going to give omega sub p equals omega sub s plus omega sub I. And momentum conservation is going to give k sub p equals k sub s plus k sub I. Or more generally, delta k is 0. And in an OPA, gain saturation occurs when pump depletion becomes important. Energy is transferred from the pump into the signal and idler, so the undepleted pump approximation fails. All right, so that's number 4. Moving along now to number 5. Okay, number 5. Okay, in a third order nonlinear medium, that third order there equals epsilon naught, that chi third order E cubed. I'll go through these, A, B, C, D. Show how 4-wave mixing terms arise from expanding the cubic electric field. Part B, 2 pump photons at frequency omega sub p generate signal and idler photons satisfying 2 omega sub p equals omega sub s plus omega sub I. Derive the phase matching condition. Part C, explain degenerate versus non-degenerate 4-wave mixing. And part D, discuss practical applications of 4-wave mixing in photonic systems. Okay, so if we have 4-wave mixing for a third order medium, okay, we get that following what we were given up here. Let the total field contain pump, signal, and idler waves. And E equals E sub P plus E sub S plus E sub I plus CC. When E cubed is expanded, terms such as E sub P, E sub S star appear. So here, this term has frequency omega sub I equals 2 omega sub P minus omega sub S. So 2 omega sub P equals omega sub S plus omega sub I. The phase factor is E sub I times this quantity, parentheses, 2k sub P minus k sub S times Z minus, parentheses, 2 omega sub P minus omega sub S, close parentheses, T. And for efficient generation of the idler, k sub I equals 2k sub P minus k sub S. So equivalently, delta k equals 2, k sub P minus k sub S minus k sub I equals 0. In degenerate 4-wave mixing, the 2 pump photons have the same frequency. In non-degenerate 4-wave mixing, the pump photons can have different frequencies, given here by this equation. All right. And applications include wavelength conversion, entangled photon pair generation, optical signal processing, frequency combs, and parametric amplification in fibers and integrated waveguides. So that's number 5, and here's number 6. Okay, number 6, an intense pulse propagates through a Kerr medium with intensity-dependent refractive index, n equals n naught plus n sub 2 I. Derive the nonlinear phase shift accumulated over distance L. Part B, that's A. Part B, show qualitatively how self-phase modulation broadens the pulse spectrum. Part C, explain the origin of frequency chirping. Part D, starting from the nonlinear Schrodinger equation, discuss the balance between dispersion and nonlinearity leading to optical solitons. And part E, distinguish between bright and dark solitons. Okay, so this is a self-phase modulation and optical solitons problem. Okay, so let's see here. Refractive index is n equals n naught plus n sub 2 I. The optical phase is accumulated over this distance L equals phi. L is phi equals omega over C and L. So omega is, phi, my apologies, phi is omega over C, quantity n naught O plus n sub 2 I, parentheses L. The nonlinear phase shift is this phi n L is omega over C, n sub 2 IL equals k sub naught n sub 2 IL. For a pulse, I equals I of t, so phi n L of t equals k naught n sub 2 Li of t. And we get the instantaneous velocity is omega sub inst equals omega naught minus this derivative here, that d phi n L dt. Okay, so therefore we get delta omega of t equals negative d phi nl dt. The leading and trailing edges of the pulse acquire different frequency shifts. This produces spectral broadening called self-phase modulation, and the nonlinear Schrodinger equation has the form, very famous here, I partial a with respect to z minus beta sub 2 over 2 times the second partial derivative of a respect to t plus gamma magnitude a squared times a equals 0. This dispersion term spreads the pulse. Nonlinear term changes the phase through the Kerr effect. And lastly, here a soliton forms when the dispersive broadening exactly balances the nonlinear phase modulation. Bright solitons occur in anomalous dispersion with focusing nonlinearity. Dark solitons occur in normal dispersion with an intensity dip on a continuous background. Okay, so that's number 6. And let's move along to 7. Okay, number 7, consider a single electromagnetic cavity made of frequency omega. Part A, starting from the classical Hamiltonian of the field, show its equivalence to a harmonic oscillator. Part B, quantize the field by introducing ladder operators A hat and A hat dagger. Derive the Hamiltonian here, which are given H hat equals H bar omega times the quantity A hat dagger A hat plus 1/2. Define the Fock states there, where we have that ket n, and show the following for that A hat dagger, that ket n. Okay, A hat, technically A hat dagger acting on n ket. Sometimes I'll pronounce it a little differently just for brevity. Equals this for ket notation. I'm just going to leave. I'm not going to say all of it. It's right there. So, and discuss the physical meaning of vacuum fluctuations. So, quantization of the electromagnetic field. The single cavity mode behaves like a harmonic oscillator. Its classical Hamiltonians can be written as follows. H equals 1/2 times that quantity there, P squared plus omega squared Q squared. Quantization promotes Q and P to operators satisfying this. This Q hat, P hat equals I H bar. We define the operators as this. A hat is square root of omega over 2 H bar Q hat plus I over square root of 2 H bar omega P hat. A hat dagger equals square root of omega over 2 H bar Q hat minus I over square root of 2 H bar omega P hat. So they obey this A hat comma A hat dagger equals 1, and the Hamiltonian is going to become H hat equals H bar omega times the quantity A hat dagger A hat plus 1/2. Okay, and if we define the number operator n hat equals A hat dagger A hat, the Fock states satisfy this. Okay. Ladder operators act as the following. These two, which we were, similar. We were given one up here, that A hat ket n, or A hat acting on n ket. People pronounce it differently a lot. And the energy eigenvalues are E sub n equals that H bar omega of n plus 1/2. And then we're given this vacuum state that 0 ket has energy E naught equals 1/2 H bar omega. This non-zero ground state energy is the vacuum fluctuation energy. Very important. Even with no photons present, the electric and magnetic fields have quantum fluctuations. Very important idea there. Okay, so that's part 1, 1 through 7. Part 2 is next. Thank you.